So we're doing RL for optimization. And last time we ended with we finished Monte Carlo, and we started up the TD-based optimization. And we had this as our initial schema, where we would take an explore exploit action. So, and the issue here is we're learning a V function. We're learning a value function. And we know we've said many times, if you have a value function, you also have to have a transition model to decide on the greedy action for your policy. And you need that for your explore exploit policy, in particular for the exploit part. And we looked at this and we said that this is going to be a convergent algorithm, assuming that your explore exploit policy is one of these GLEE policies that ends up being greedy in the end, and that the learning rate parameter is annealed at the proper rate, not too fast and not too slow. So, and this was really, if you think about it, it's kind of surprising. I've tried to make this point that I don't know if you also find it surprising, but if you think about what temporal difference learning is doing, right, you're starting off like with no knowledge at all. It's like I take one of you and you just come up with a random value function in your mind, right? And then the only thing that's driving learning is you're at one step and you say, well, what do I think the value of this state is, like my crazy value function? And then you look ahead, you get one extra experience, and you see, well, what does my crazy value function think about the future? And that's basically how you get your estimate, R plus VS prime, of what the value right now should be. And you try to make those values consistent. So you try to make your one-step prediction consistent with your current prediction. And even though that you might have this crazy value function that you start off with that means nothing, this still converges. And it still converges. The other thing that's pretty interesting is like this policy is evolving all the time, right? And the value function, we're learning. You're trying to learn the value of this changing policy, and the policy depends on the value function. It just seems very circular. But like we said, it converges, and largely because of the contraction properties of the MDPs. So the problem here is that we have to have the model, and we don't want that because when we go to generalize this to function approximation, where we're not going to have a table for the value function, it's going to be much harder to, for example, train a neural network to learn a value function and then use it to make decisions, because you're going to have that transition model still. And in a large state space, that's something you would have to learn as well in some cases. When you don't have to learn it, when you have the model, maybe this is okay. But we want to handle cases where learning the transition model, we don't want to require ourselves to learn the transition model or even use it when we're making decisions. And so the idea now is, can we do something like this, TD learning, but learn a Q function instead? Right? And if we learned a Q function instead, then if we're in a state, all we have to do is maximize over the actions and we take that action. We don't need a model. It's sort of baked into the Q function in some sense. And then you could imagine, we can use a neural network to learn a Q function. And that's what people do. You get algorithms like DQN. So that's where we're headed. So we're looking for a model-free variant that learns Q functions. And last time I said we're going to look at two approaches in turn. And one approach we're going to think of as being a approach derived from generalized policy iteration. This generalized policy iteration, when you have the model, basically it can just randomly pick a state and either do a step of policy evaluation, like one little backup for policy evaluation, or one little Bellman backup for policy improvement. And it can just randomly make these choices. And as long as it keeps on making these choices, along with there's some other little technical conditions we won't get into, it will converge. And so the SARSA algorithm, which we're going to introduce, is basically taking that algorithm roughly speaking, and doing a stochastic approximation, right? So expectations that are computed with the model are now going to be just dealt with via samples by acting in the environment. And the second approach is going to give us Q-learning, very famous algorithm, and that you get by starting with value iteration and doing a stochastic approximation. Okay? So hopefully we can get through these this lecture, because these are going to be the topic of your next homework assignment, which we'll probably get that out tomorrow night or Wednesday, sometime in the afternoon. And you're going to be doing implementing Q-learning and SARSA and distributed versions of those. And the one after that is likely going to be similar, but you're going to be using neural networks and solving larger problems. So that's probably what everybody is here to do in the first place. But we're going to go through these other exercises first. All right. So any questions before we get into this? All right. So that's the context. So now let's see. We're going to start by figuring out how can we use MC, Monte Carlo, or temporal difference learning to learn a Q function, right? And so we're going to study this first, assuming we have a fixed policy. So we want to learn a Q function for a fixed policy. And just so I make sure people understand, what does Q pi SA mean? What's the meaning of that? It returns a number, but what does that number mean? Anybody want to articulate that?
Isn't it the value you would get from taking that action within that state and then following that policy?
Yeah, exactly. So Q pi SA is the value, the long-term infinite horizon, discounted expected value that you get if you're in state S, you take action A, and then you follow the policy, right? Action A may or may not be the one that the policy would have chosen. So it's sort of a one-step departure from the policy. And we all know that policy iteration gets an improved policy by maximizing this, right? So we're going to study that first. We're going to see how to do this. And then, like we saw for TD learning, we can just apply that algorithm to now a policy that's evolving, right? That we're going to apply it to an explore-exploit policy, and it's going to magically converge, right? Even though it's not clear beforehand why we should expect it to. So that's what we're going to do now. So let's look at this problem. So what we're going to be given is the ability to generate observed episodes of a fixed policy. And we're going to want to output the Q function for that policy. So MC and TD. So let's remember what we did for Monte Carlo when we were learning the value function. So all we did was we generated an episode, and then for every state, the first time you get to it, you look at the future return, and we just averaged all the future returns that you got from a particular state. And so that was pretty straightforward. You just, whenever you're in a state, you see, well, what did I get when I, in the future? You just average all of those. And that will converge because expectations converge to averages converge to expectations. So that was straightforward. So we can adjust this to learn a Q function very easily, although there's going to be a little caveat here. So what we're going to do now is, so the Q function depends on S and A, right? And so we have to condition what we learn on S and A. And so you generate this sequence, and for each SA pair, and we're going to again do the first time a pair appears, we're going to average, we're going to look at what was the return that we got after you took A and S, and we're going to just average those. Every time you see state S and action A taken, you're going to average all the future returns. So that's pretty straightforward, intuitive idea. Does that make sense to people? Does anybody see a problem with this if we want to learn a full Q function with this approach? So what does it mean to learn a full Q function? Right? If you're my oracle for the Q function, I want to be able to give you any S and any A and get a number back. Right? Will this accomplish that? Yes, no? Anything missing?
So in this, you're only taking actions from your policy,
Right.
So then you could function on the
Right, right. So what he's saying is that these sequences are generated just from the policy, right? And so if we're using a deterministic policy, are you going to learn a Q function using this routine that handles all actions? You're only going to learn a Q function for the actions that the policy takes, because you'll never have any other actions in this data, right? So that's a problem. That's one of the fundamental problems of trying to evaluate a Q function given a fixed policy, right? And so that is basically what this says. And so I think this is just answering that. So how do we deal with this? Well, one way of dealing with it, maybe it's satisfactory, maybe it's not, but there are different ways. But in our framework, where you're just executing in the wild, what's often done is you're going to consider stochastic policies. So we're going to learn Q functions for policies that are not deterministic. And why do we care about that? Well, when we eventually do explore exploit, and we're learning from explore exploit policies, you can view those as sort of not being deterministic, and they will consider all actions, and so they are stochastic in a sense. And so we're going to consider, well, what if the policy is stochastic, and then applying this. So we haven't talked about stochastic policies yet, so we'll spend a minute on that here. We'll deal with them later on as well when we talk about policy gradient. But a stochastic policy is just a function pi that for any S and A returns a probability of taking action A in state S. So it's a stochastic controller. And a deterministic controller is a special case of this, where one of the actions gets probability 1 and the others get 0. And of course, all of the, since it's a probability function, the sum over all the actions has to be 1. Right? So you can get a completely random controller by assigning equal probability to all actions. It's probably not going to be a good one, or a deterministic one. And to follow it, when you end up in a state, you sample an action from the policy's distribution, and you take it. And everything we've learned about the values of policies and optimization hold for stochastic policies. You just have to put in an extra expectation. We're not going to go over the details of that. And in fact, the book just starts out with this at the start. All the notation is in that way. So for learning the Q function of a policy, if we have that for every action, the probability of that action is non-zero, right? Eventually we'll get examples in the data set where in every state you've tried every action. And then we can learn Q values for all state action pairs. Does that make sense? So it's not quite satisfying because we're not really learning, we haven't given a solution for deterministic policies. But the SARSA approach that we're going to discuss basically gets around that by focusing on stochastic policies. And like I said, during optimization, we're going to be following this explore exploit policy, which is stochastic by nature. And so it does get coverage of all the actions. All right. So then we basically have the same exact code. Right? You're going to generate trajectories, except now you're going to have some stochastic policy, and then you run this code. And what you can say is that if you run this forever, these values are all going to converge to the true Q values for every state action pair. Because you will have tried every state action pair infinitely often, and seeing the return that occurs after them, and that return is from a fixed policy. So any questions about this? Right, this is the Monte Carlo approach. So yeah, that's and TD is a very similar. We can do a similar thing for TD. This is showing you the TD equations for the value function, which we've already gone over today. We can adjust these to update based on the Q function. So let's look at that. So here's the TD rule. Let's see how we update it. So this is the TD rule on the previous slide that was in the code. And this is a key identity that we're going to follow. So v pi of s, the value function at s for pi, is equal to this. The Q function at s evaluated at the policy's action. Does that make sense? Kind of make sense to people? Yeah. Because yeah, that's basically that's saying, well, what's the value if I take the action of the policy and then follow the policy? Well, it's the policy's value. And then you could adjust the updating rule this way here. Okay. And again, this is just a noisy sample of the Q function. All right, so you're going to choose this, and yeah, instead of we're going to be sampling actions from the policy. That's another approximation here. So this is the adjustment to TD. Now, whenever you take an action A and observe R and S, you're going to do this update. And it's the same intuition as for the value update. Right? This is your R plus Q pi S prime A prime. That's your estimate of your improved estimate of the Q value. And this is your current estimate, and we see this is sort of the error, right? And so this is the same form that we've seen before. So any questions about this? Right? And if it's a stochastic policy, this will converge. This will work out. All right, so we know how to learn a Q function given a fixed policy now, and in particular a stochastic policy. We haven't said what to do if it's a deterministic policy. And now we'll just apply these algorithms kind of blindly, because we've seen it work before, to an explore-exploit policy. And this is what you get. I'm not actually going to write this out for Monte Carlo, because it's pretty straightforward. I'm going to write it out for TD, and this gives you a very famous algorithm called SARSA. So SARSA does nothing more than you take an action according to your explore-exploit policy, and then you do this simple update, and you just keep on repeating over and over and over. All right? So that's pretty simple algorithm, right? It's not really any more complex than that TD algorithm we showed. Just you have to do a little more bookkeeping. You have to keep track of S and A as opposed to just S. So any questions about this? All right. And amazingly, this converges to the optimal Q function if you have this GLEE exploration policy and the alpha learning rate is adapted correctly. Okay, so this is another one of those situations where it's kind of surprising it converges, but it does. And why is it called SARSA? Right, that's one interesting thing. Well, it's called SARSA because the tuples that we learned from are S, A. Right, we were in state S, we took action A, and we saw reward R. We ended up in state S prime, and in S prime we took action A prime. Right, so SARSA. I guess they were pretty proud when they noticed that. It's something that's pronounceable, sounds kind of cool. It's always a nice feeling when that happens. But that's why it's called SARSA. And a lot of learning algorithms don't use that next action, right? SARSA uses that next action because it's on policy. We call this an on-policy learning algorithm. It's learning the value of the current policy, and we're just adjusting that policy to get more and more greedy over time. All right. So yeah, and you can read this one on your own. It's not surprising. You just do Monte Carlo Q function learning, and you follow an explore exploit policy instead. And like last time, for very technical reasons that well, people don't really understand why, but the convergence is not settled fully. So TD is fine, but for some reason they can't solve this problem yet. All right, so that's it. So that's how you derive SARSA. Right? There's if you've heard about SARSA before, basically it's we refer to it as on policy because it's learning the value of the current policy that's being followed. And it just so happens that if you adjust that current policy just right towards a greedy policy, it will learn the value of the optimal policy at the end. All right. So any questions about SARSA? Right. Pretty easy to implement. Just a few lines of code. You'll be implementing it, so you'll get some experience with this. So now we're going to look at Q learning, so off policy learning, and so it is worth mentioning just a few points about on policy learning, though I would say. So I guess I'll stick here just for a few more minutes. So one thing that happens in on policy learning, which can be annoying and can be quite it can be bad in a lot of cases, is we're learning the Q function for the explore exploit policy, right? And does anybody see anything that might be bad about that, like from a practical standpoint? Right. So what's an example explore exploit policy? Epsilon greedy, right? You have an epsilon, and every now and then it takes a random action with epsilon probability. You're learning the value function for that policy, right? The epsilon greedy policy. And in SARSA, if you fix epsilon, it will converge to like the optimal policy that randomly takes an action every epsilon with epsilon probability. But you can imagine, who can think of a situation where the best policy that randomly takes an action with epsilon probability could be very different from sort of the best deterministic policy? Right. So I'm saying I'm gonna let you find the best way of taking actions, but under the constraint that you have to let me with epsilon probability take a random action from time to time.
There might be cases where there's some extremely bad actions in some states, but because you have to sample them, it can really bias the estimate of the value of that state. So
right.
It might be fine on average, it might be a really nice sort of shallow reward, but there's really awful failure states nearby.
Mm-hmm. Yeah, this can actually cause you to change, like the policy you'll end up learning is going to be different. So imagine, I'm trying to get over there across the room, and there's a nice little pathway right across the room, but there's 3,000 feet on each side, down on each side. So if you fall off the pathway or walk off the pathway, you're done. But otherwise, it's just a straightforward walk across, and you have even deterministic actions that will get you there with 100% probability. You also have actions that cause you to walk sideways either way, right? The best deterministic policy would not walk sideways and fall off the cliff, right? So there's a nice deterministic policy that just goes right to the end of the room there, and does not fall off the cliff. But what if with epsilon probability, somebody's going to take a random action? You're going to be a little nervous about walking across that narrow path, right? Because with some probability, you're going to fall off. And if the path is long enough, you're definitely going to fall off, because at some point, your luck's going to run out. They'll pick a random action, and you'll go to the side and fall. So what would happen if you're doing this with SARSA? let's suppose there's a direct path there, but there's a really roundabout path that there's no cliff to fall off. SARSA will tend to choose that because it would sort of learn, oh, going across this path is dangerous because I'm learning the value of a policy with exploration turned on. And so you can actually learn very different policies when there's bad failure states that random actions can get you into. And that's one of the, we've run into this in our research. That's one of the difficult things about using SARSA, in my experience. But there are plenty of domains where that's not really an issue. You don't have that sort of structure. But it's just something to be aware of. It's a pretty subtle point until you see it the first time, and then you're like, why is it going all the way across? Oh yeah, it thinks that it's going to be taking random actions, and it's planning for that, right? So it's a rational thing to do, right? You would not walk across that cliff if I said I'm gonna. You could get pushed either side randomly. You would not do that either. So, all right. So that's a general phenomenon for on-policy learning, basically, when you're doing optimization. So, any questions about this? All right. So now we're going to do off-policy learning, and this is pretty interesting because basically what we're going to get is an algorithm that you can give it any sequence of data experiences that you want. They don't even have to come from a consistent trajectory. And as long as you get all experiences infinitely often, right? As long as you touch all states and actions infinitely often, this will converge. So it's called off policy because you don't have to follow a particular policy. This algorithm is not trying to evaluate a policy. It's using experience to try to directly learn the optimal Q function. Right? And so that's why they call this off policy. And these can be very useful algorithms because you can sort of get your data any way you want, yet still get the optimal policy in the end. So it sort of decouples how you get your data versus how you learn the policy. And Q-learning is the most famous of these algorithms. So Q-learning basically derives from asynchronous value iteration. So let's review that. Really simple. You repeat forever, select a state, do a Bellman backup. Do that forever, and we've said that this will converge to the optimal value function. Of course, this requires that you know the reward function and the transition function. But we've already talked about how you can replace this transition function with a sample, right? Just a sample. That's the stochastic approximation. That's where we got the TD learning algorithm. So what we'd like to do is sort of get a version of asynchronous value iteration, but for learning Q functions. For not learning, but for computing Q functions. If we had the model, then we'll do a stochastic approximation of that. Right? So instead of value iteration, we're going to have Q iteration, right? An algorithm that iterates on Q functions instead of value functions. So let's look at that. So this was asynchronous VI, and the update looks like the Bellman equation. We've gone through that before. Now we can turn that into sort of an equivalent update for the Q function, right? So it turns out that the optimal Q function, okay, so we're just writing things out here. So the optimal Q function, remember, this is the Q function for the optimal policy, is equal to this RSA plus sort of the expected optimal value after you take that action A. All right? So this is just sort of definitional here. And the key thing to realize is that the optimal value function at S prime is equal to the max over all actions. Right? So down here, I'm showing you the basic equality that we're using. So the optimal value function, the optimal value of state S is equal to the max over all actions of the optimal Q function. Does that make sense? Right? And this max is going to happen at an action of an optimal policy too. So So this is almost this is the Bellman equation, effectively. Like the Q function expands to, if you expand this out, you're going to get the Bellman equation. So this is an equality, and we can take this value function out, replace it with the Q function. So now we have basically a Bellman equation that only involves the Q function. So that's nice. And now we could, I mean, after a while, you just use your pattern matching and you say, oh yeah, I've got this Bellman equation. I can now just come up with an asynchronous update, and it's probably going to converge. You can prove that it converges, but we've seen this pattern quite a bit now. So the asynchronous update is going to be you pick an S and an A and you update in this way. This is like the Bellman backup for a Q function, right? And the main difference is instead of just updating at a state S, you update at a state action pair. But there's really no significant difference beyond that. Okay? And you only need to have the Q function because we can write this value in terms of the Q. Right? So is this okay so far? Right. And that gives you an algorithm. So asynchronous Q value iteration. So you randomly select a state, you randomly select an action in that state, and you do this update, right? And if you do that over and over and over, and you make sure that you always have a chance of selecting every state action pair infinitely often, this will converge to the optimal Q function, all right? So from value iteration to Q iteration. And now it's a simple matter to say, to look, again, our pattern matching, we've seen this before. We're going to do a stochastic approximation of the expectation here. And, based on our pattern matching, we probably believe that might converge. So Q-learning is nothing but an algorithm that starts with this, and it replaces this expectation with this thing here as being the target of the TD update. We'll show that algorithm in a moment. But if you took an action in state, if you took A in state S, you observed R, and you ended up in S prime, this is going to be your sort of estimate of what QSA should be. And this is the Q-learning algorithm. And we'll compare this to SARSA in a moment. They're deceivingly similar. But you just keep going around this loop. Every experience you get, you do an update, and that's all there is to it. So you have to do this little max over the current Q function. And this is guaranteed to converge. For any way of producing data, like here I'm saying choose an action via an explore exploit policy. Like this is in the context of like running episodes in an MDP, but it doesn't even have to be like consistent episodes. As long as you have a way of generating state action experiences, and as long as you generate all such experiences infinitely often, this will converge. So any questions about Q-learning? Right, because that's a very simple algorithm. This was developed in, I think, 89. The proof of convergence was a little more complicated then, but then people simplified it by using stochastic approximation theory. So the first proof was very, very special case for Q-learning. Then people said, oh yeah, there's this whole field of stochastic approximation theory, and this is just a special case of that. And there are nice, if you search for convergence of Q-learning, you'll find these papers. All right. So it's worth, comparing SARSA and Q-learning because they look very similar. So this is the only difference. Right? So Q-learning is going to use a target that's maximizes over the actions, A prime. And SARSA uses a target where A prime was the action that was taken by the policy in S prime. And remember, when we're running SARSA, this is going to be an explore exploit policy. So when SARSA is exploiting, right, it's picking the A prime that maximizes the current Q function. And so it's going to sort of do the same update as Q-learning, right? That's what SARSA will do. And so they only really differ on these explore actions that go against the current greedy action. And so that's where they differ. And that's actually the key thing. Like that's the action that made me fall off the cliff. Right? I fell off the cliff by stepping right with my exploration action, and Sarsa is going to update based on that. Falling off a cliff might give you a reward, a really bad reward. Whereas, Q learning is not going to really worry about falling off the cliff so much. Let's see. Yeah, I've kind of talked about these before. So yeah, I think we've discussed all this text. You can look at it at home. And that's Sarsa and Q learning. So any questions on this stuff? You'll be implementing both of these, and yeah, I'm kind of curious to see what's going to happen in your. I think we're using the same domain, right? Frozen lakes, I believe, and frozen lakes kind of has this. It's got holes that you can fall into, so it kind of has this property that I was talking about. That Sarsa might learn like a more conservative strategy, right? It will kind of want to stay away from holes a little more than Q learning. So it'll be interesting to see if that actually materializes. All right, so very good. That basically prepares you with the basic algorithms for the next assignment. There's a few little additions that your book talks about that I think is worth mentioning. So one is there is a version of Sarsa that is off policy. So you can do updates based on any data. And basically, so Sarsa, this is the Sarsa update. It's just based on a single state action pair. Whereas expected Sarsa, the thing is when we know what the policy is, and we know so this is going to be an explore exploit policy, typically when we're learning, but you can figure out the probability of every action that the policy might have taken, right? And generally, for an epsilon greedy explore exploit policy, there's going to be probability 1 minus epsilon for the greedy action, and then the epsilon probability is distributed across the others. And you can compute the expected Q function. The expected, this is sort of an estimate of the value at S prime, right? Because you're looking at the expectation over actions the policy might have taken. And so this completely decouples you from this particular action that the explore exploit policy took, right? Because this expectation goes over all actions. And hence, this is referred to as an off-policy version of Sarsa, expected Sarsa. And this can work pretty well. But yeah, it's you can learn off policy, and that's the big selling point. This is just another comparison: expected Sarsa versus Q learning. You can see if you put all the probability mass on the best action, you end up with Q learning updates, right? If all of this probability mass is on the max action, you end up with the same equations here. Now your book, they've got some figures that. So your book, you might say they're a little bit biased towards Sarsa, because Rich Sutton developed Sarsa, and Andy Bartow, who was his advisor. They wrote the book, so they're big on Sarsa. Not to say they don't like Q learning, but their figures they've got this figure in the book 6.3, which is showing expected Sarsa doing better than Q learning. And but if you look if you look a little more carefully, what you see is that what they're plotting for performance is the performance of the algorithm with exploration turned on, right? So often when you're plotting performance of a reinforcement learning algorithm, you'll learn for a while, like with exploration. But when you're actually evaluating the policy, you're saying how good is it? You'll turn exploration off and just run the policy, right? Because we're not going to, in the real world, generally want to have it exploring when we're actually trying to use it for utility. And so that figure is actually with exploration turned on. So, that's a caveat I would say about that claim in the book. But it's an interesting algorithm. I don't have much experience with expected SARSA. All right, your book also talks about importance sampling. I'm not going to talk about that here. It's pretty horrible. So it's one way. It's a generic way to do off-policy Monte Carlo. Monte Carlo has to kind of be on policy because you're estimating what did that policy actually achieve, right, in a run. And I'm just gonna ignore this. It's pretty bad. Lots of numerical issues. I've used it before, but it's a pain. So we won't cover that. This is a very good trick that people use. So this is sort of goes under the bucket of tricks. N-step bootstrapping. And I think to do this justice, it's going to take me a little more than 2 minutes, not much more, but I think we're at a good point to stop today. We'll just finish up this tomorrow or Wednesday, and then I think we're going to be moving to function approximation. So what everybody might have been waiting for, deep reinforcement learning. All right. So we'll see you on Wednesday.